So let's now turn our attention to part 2 of the additivity property and proving that second part. So firstly, let me just remind you of what the second part said. Here is our interval AC, and this time we start with the assumption that the function is Riemann integrable over the entire interval, and of course we'll call the value of that integral the integral of f dx over AC. And now that second part of the additivity property said that if we take any point in between A and C, and we'll call that point B, and use that to split our overall interval into two subintervals, the interval AB and the interval BC, then the function is going to be Riemann integrable over the interval AB, and it's going to be Riemann integrable over the interval BC, if it's Riemann integrable over the entire interval AC, and the value of those two integrals added together will make the value of this integral. Now that last bit that I've just said, we already know that by part 1. If we show that it is indeed true that if the function is Riemann integrable over the entire interval, then it's going to be Riemann integrable over the two subintervals, then we know that final bit, that the value of those two integrals over this interval and this interval makes the value of the integral over the entire interval by what we've already shown in part 1. So actually all we need to do is show that if the function is Riemann integrable over the entire interval AC, then it is also Riemann integrable over the two subintervals AB and BC. And that's actually not too difficult to do. We'll use the Riemann integrability criterion. So we're going to show that the function is Riemann integrable over the interval AB and the interval BC by showing that it obeys the Riemann integrability criterion over both. Now, for simplicity, let's just focus on one initially, and we'll focus on this interval AB. And let's remind ourselves of what the Riemann integrability criterion says. So it says, written out in full formality, for all epsilon greater than 0, there must exist a dissection, and remember we're talking about the interval AB, so this is a dissection just of that interval AB, such that the difference between the upper Riemann sum of the function over that dissection and the lower Riemann sum of the function over that dissection is less than that value epsilon. So whatever epsilon you take, however small it is, as long as it's a positive real number, you must be able to find a dissection such that this is true. If the function is Riemann integrable, this is satisfied, and it's an if and only if relationship. So we proved that in the previous video, the video on the Riemann integrability criterion, that this is an equivalent statement to the Darboux definition of Riemann integration that we have seen. So this is what we need to show, and then we'll have shown that the function is indeed Riemann integrable over that interval AB. And really what it's saying is that you can find dissections such that the difference between the upper and lower Riemann sums are indefinitely small. That's what this for all epsilon greater than 0, the difference between the upper and lower Riemann sums is less than epsilon, is capturing there. So how are we going to show that that is true over the interval AB? Well, really we're just going to have a play around, and the only bit of information that we've got to play around with is of course that the function is Riemann integrable over the entire interval AC. And what that means is that the function is going to satisfy the Riemann integrability criterion over that entire interval AC. So if we now extend this dissection to being over the entire interval AC, this is satisfied. It must be, because that initial assumption is that the function is Riemann integrable over that interval AC. Now, surely we would be able to use that to our advantage. If we're trying to show that this holds true for the interval AB, surely we could use the fact that this holds true for the entire interval AC to do that, because these upper and lower Riemann sums over the entire interval AC, they contain upper Riemann sums and lower Riemann sums over just that smaller part of the interval AB. So surely we could use the fact that the overall, the larger upper and lower Riemann sums over the entire interval, that the difference between them is less than epsilon, we could use that to surely get some information about what the upper and lower Riemann sums restricted just to this subinterval are, what the difference between them is going to be. So that's our sort of plan. So here then is the proof that the function does obey the Riemann integrability criterion over the interval AB, if it obeys the Riemann integrability criterion over the entire interval AC. So we will let epsilon be greater than 0, and we're now going to show that we can find a dissection D such that this is true. Now, for our epsilon greater than 0, we can now apply the Riemann integrability criterion for the entire interval AC and say that I can find a dissection D that is a dissection of the entire interval. So it's not just a dissection of the interval AB, it's a dissection of the entire interval AC that will obey the fact that the upper Riemann sum minus the lower Riemann sum is less than epsilon. And my hope from this is to be able to construct a dissection just of the interval AB such that when we use that dissection and create the difference between the upper and the lower Riemann sum over that smaller dissection of the smaller interval, it will still be less than epsilon, and it's going to work. So, how am I going to do this? Well, what will help is drawing a picture of this dissection D. So here is my interval A to C. Let's put on the point B here, and now let's mark on the cuts of the dissection in blue. So these are the cuts of this dissection. They might look something like this. Now, if you're very lucky, your dissection might actually contain the cut B. B might actually be a cut in this dissection. However, in general, that's not the case. So in general, we might have to add B in because the lack of B is causing us a problem at the moment. Because really what we want to do is split this dissection into a dissection of the interval AB and a dissection of the interval BC, and then we can write these upper and lower Riemann sums as the sums of the upper Riemann sums and lower Riemann sums over the subintervals with their dissections. So we want our dissection to contain the point B because then we can split it up in this way. So if it does contain it, fantastic. If it doesn't, just add the point B into the dissection. So create a new dissection, D bar, where D bar is equal to D if D already contains B, and if it doesn't contain B, then D bar is equal to D with the additional cut of B in it. Now, this new dissection is a refinement of the original dissection D. Either it's equal to the original dissection if B was already in it, or if B wasn't in it, it's a refinement. And therefore the upper and the lower Riemann sums are going to be better. So we know from our study previously of upper and lower Riemann sums that the upper Riemann sum over a refined dissection is going to be less than or equal to the upper Riemann sum over the original dissection, and it is going to be greater than or equal to the lower Riemann sum over that refined dissection, because upper Riemann sums are always greater than or equal to their lower Riemann sums, and that lower Riemann sum is going to be an improvement of the lower Riemann sum of the unrefined dissection, meaning that it's going to be greater than or equal to it. So this relationship holds true. So now I'm going to take this inequality and I'm going to create an inequality for my new refined dissection. So if this one minus this one is less than epsilon, well, these two are inside of those two. So on the number line, it looks like this. In fact, we'll color code it. So in green, these are these old ones. Clearly this one is the lower Riemann sum, and this one is the upper Riemann sum. And these ones might, now that I'll put in yellow, now these might actually be equal to the original ones. It might be the case that this additional point being added in might not change the values of the upper and lower Riemann sums at all. That might happen. Or indeed it might be the case that B was already in it and therefore D bar is just equal to D. So they might be equal to them, or they might be actually inside like this. But the point is that they're either equal to them or they're inside. They're not outside, and therefore the difference between these two is guaranteed to be less than epsilon also. So the argument that I've just given you there is that for this refined dissection that has the point B included, this inequality is also going to hold true. So overall, what I've done is I started with my epsilon that was greater than 0. I used the fact that the Riemann integrability criterion holds over the entire interval AC to find a dissection such that this was true. I said if that dissection contains B, fantastic, we're in business. If it doesn't contain B, then create this new dissection D bar, and we'll call D bar D if it did contain B, so that we can just keep our notation consistent in the future. But if it didn't contain B, then you've added B into this dissection, and now with this new refined dissection, the inequality is still going to hold true, that the difference between the upper and the lower Riemann sum is going to be less than epsilon, and that's because it is a refinement of the original dissection. So the upper and lower Riemann sums have actually got closer together, most likely, from that refinement. At the very worst case, they have stayed the same distance apart as the distance between the upper and lower Riemann sum of the less refined dissection. But this inequality is still going to hold true for my dissection D bar. So now I can split D bar then into two separate dissections, a dissection of the interval AB and a dissection of the interval BC. So we'll call that D1 and D2. And by the arguments that we've given previously in this video on the additivity, we know that the upper Riemann sum over D bar of F is just equal to the upper Riemann sum over D1 of F. So that's an upper Riemann sum for the interval AB using this D1 dissection, which is the points of the dissection D bar that are in the interval AB, plus the upper Riemann sum of F over D2, which is an upper Riemann sum over the interval BC. Similarly, the lower Riemann sum over D bar of F is equal to the lower Riemann sum over D1 of F, which is a lower Riemann sum over the interval AB, plus the lower Riemann sum over D2 of F, which is a lower Riemann sum over the interval BC. Now what we can do is just substitute those into this inequality and just rearrange it a little bit to put the appropriate upper and lower Riemann sums next to one another. So we'll get upper Riemann sum over D1 of F minus the lower Riemann sum over D1 of F plus the upper Riemann sum over D2 of F minus the lower Riemann sum over D2 of F is less than epsilon. So I just substituted in this for this and this for this, and then just collected the terms where we're talking about sums over the same interval with the same dissection. So this is the difference between the upper and lower Riemann sums for the function over this interval AB using that dissection D1, and this is the difference between the upper and lower Riemann sums over this interval BC using this dissection D2. Now, I can therefore conclude that if we take this dissection D1, which is a dissection of the interval AB, that the difference between the upper Riemann sum and the lower Riemann sum is going to be less than epsilon, which is exactly what I wanted to do because I've now found a dissection such that the difference between the upper and lower Riemann sums is less than epsilon, and the dissection that is over the interval AB. So D1 is a dissection of the interval AB. Now, why can I conclude that from this line? Well, it's because if you take the difference between an upper and lower Riemann sum, it's always going to be positive, or positive or zero, because remember, any upper Riemann sum is always greater than or equal to the lower Riemann sum over that same dissection, or indeed it actually holds more generally. Any upper Riemann sum is always greater than or equal to any lower Riemann sum. They don't even need to be over the same dissection, but it certainly holds true if they're over the same dissection. So this is some positive number. So if this plus a positive number is less than epsilon, then certainly this on its own is size less than epsilon. So this is actually less than epsilon minus some positive number, and of course it's a positive number as well, so we know it's greater than 0. So that's how we can conclude that this bit is less than epsilon from this. And in fact also here we have shown that the same thing is going to be true for the interval BC, because we can also conclude that the upper Riemann sum over D2 of F minus the lower Riemann sum over D2 of F is less than epsilon for the exact same reason, because this has to be a positive number, this also has to be a positive number, so it's something greater than 0. What's it bounded by above? It's bounded by epsilon minus this positive number, so it's certainly bounded by epsilon therefore, so we can conclude that it's less than epsilon. And therefore, I've managed through this same argument to construct a dissection of the interval BC. Remember, D2 is a dissection of the interval BC such that the difference between the upper and the lower Riemann sum is less than epsilon. And you could have done this argument for whatever epsilon you like. So in this way, I can construct, with whatever epsilon I like, I can construct dissections of the interval AB and the interval BC such that these inequalities are satisfied, and since it holds true for any epsilon greater than 0, I can hence conclude that for all epsilon greater than 0, there will exist dissections of these intervals AB and BC such that the difference between the upper and lower Riemann sums are less than epsilon. So hopefully you understand that. The Riemann integrability criterion is going to be satisfied over this interval AB, and it's going to be satisfied over this interval BC. So we can conclude that the function is Riemann integrable over the interval AB and the interval BC if it's Riemann integrable over the entire interval AC. Now, of course, we'll denote the values of those integrals. This is how we'll denote the value of the integral over the interval AB, and this is how we'll denote the value of the integral over BC. And by part 1 of additivity, we know that if we that the value of the integral over the entire interval must equal the sum of the value of the integral over these two subintervals. So we know that if we add those two together, it must equal the value of the integral over the entire thing, and hence we have finished our proof of those two bits that we separated the additivity property up into. So I hope that has been clear. I hope you've enjoyed the video. We will end here.